Welcome! In this lecture video, we will discuss the refraction, reflection, and conversion of seismic waves from one type into another at an interface. Hopefully, this is actually a phenomenon that everyone is already familiar with in terms of light. So light is a perfect analogy for seismic waves in this case because the physics behind light being refracted is the same as the physics behind seismic waves being refracted. So we'll go ahead and start by talking about light. When you have light hit another substance like a prism, then you are going to have an incident ray. The incident ray in this image is this one coming in and being incident on this surface, causing it to bend a little bit. In the case of light, this actually also different wavelengths of light bend at different angles, which causes that light to spread out. And then when it hits this interface, it's actually going to bend again, going from the air into the glass, and then from the glass into the air, and it's going to spread out again. And so you get all of these refracted waves on the other side. So the waves coming in are called incident rays, and the waves going out are called refracted rays. How this might look like in an analogy that's a bit more similar to the seismic case. You have your incident ray going in. Maybe this is light, but maybe it's a seismic wave. It hits some boundary and refracts as it goes through into the second medium. So when we discuss the exact paths of these rays, we can refer to the angle of incidence, which is the angle that the incoming ray makes to the normal. So the normal is this line here, and that is just a line perpendicular to the interface, okay? Everything as far as the rays go, the ray angles are always measured relative to the normal. The normal is always perpendicular to the surface that you're interested in. So the incoming ray, the incident ray, is going to have an angle of incidence measured from the normal, and the refracted ray is going to have an angle of refraction measured from the normal on the other side. Here we have that again, except this time we can watch as the light goes through a piece of glass. And you can see in this case, here is the boundary, here is the normal, and the incident ray comes in, refracts at the interface, hits this second boundary, the normal is here, and it refracts on the way out. So the angle of incidence is the angle that this ray makes with the normal. So this here is the angle of incidence, and this would be the angle of refraction, and then this would be the second angle of incidence, and this would be the second angle of refraction. Okay. We can actually use Snell's law, which is a mathematical equation, we can use it to determine the values of the incident angle and the refracted angle, and all that this is going to depend on is the velocity of the wave through the medium. So if you were dealing with light, this would be the velocity of light through air and then through glass or through water, whatever you're sending that light through. If you are dealing with seismic waves, it's going to be the velocity of the seismic wave through whatever mediums you're examining. Maybe that's air into unconsolidated sediment, or unconsolidated sediment into limestone, or limestone into granite, whatever it may be. So over here, I've actually drawn a sine wave for you, but we're going to draw an incident ray coming in from this side. But if you think about it, the only possible angles that we're going to be able to consider go from 0, which would be coming in at this direction, to 90, which would be coming in at that direction. So the only part of the sine wave that we really need to worry about is this part here, describing what that wave does from 0 to 90. Now, What this equation tells us is that the angle that the incoming ray makes with the normal divided by the velocity of the wave through the first medium, so let's just say maybe it's air, is going to be equal to the angle made with the normal on the other side divided by the velocity of the second medium. So what do you think is going to happen if you send a wave, let's say it's a seismic wave, from a material that has a slower velocity, so a small number down here, and you send it into the ground into a material that has a higher velocity? What do you think is going to happen? Here's my incident ray heading straight to the normal. Which direction is it going to bend? Is it going to bend towards the normal, that way, or away from the normal, that way? Because it is going to bend. What do you think? Go ahead and pause the video for a second and give it a thought. So, if this number on the bottom gets bigger, but the entire thing stays the same, this on the top has to also get bigger. Okay, so what type of angle is going to give us a larger value? Again, we're restricted from 0 to 90, and it looks like a larger number, a higher angle, is going to give us a higher value. So in order to keep the left side of this equation equal to the right side, we're actually going to need to increase the angle. So the angle of refraction is going to be higher than the incident angle. So the incident angle is this one, measured from the normal, and on the other side the angle is also measured from the normal, which is this line here, and it's going to be larger than that incident angle. So maybe it's like that, and we have a wave that has gone to the boundary, refracted at the boundary. It's actually refracted away from the normal when traveling into a medium with velocity greater than the velocity of the first medium. So here is another example, and in this case you want to look always at the incident angle and the angle of refraction. So this would be I1 and this would be I2. And can you tell me which material has the higher wave velocity? Is it material 1 or material 2? So in this case, our incoming wave bent towards the normal, which means that material 2 must be slower, because if this number on the bottom is smaller, the whole thing on top must be smaller, which only happens for smaller angles. Okay, so that's how we know that it actually bends towards the normal when it's going into slower materials. Okay, what about this case? In this case, is material 2 faster? Is the wave traveling through material 2 traveling faster or slower than it was while traveling through material 1? Well, did it bend towards the normal or away from the normal? That's the first question. It bent towards the normal, and so that means that this angle got smaller, and that means this must also have gotten smaller. So in this case, material 2 must represent the slower material. And just one more time, which material is the faster material, material 1 or material 2? Hopefully you said material 2 is faster, V2 is greater than velocity through the first material, because this angle here, the refracted angle, is larger than the incident angle, meaning this number went up So the whole thing must have gone up, and in order to keep those two sides equal, the number on the bottom must also have increased, so the velocity in the second medium is faster than the velocity in the first medium. And here again, we actually are hitting with a larger incident angle, and that's causing even more bending of the ray. And so again, this V2 is greater than V1, and you can see as this angle is sort of increasing, the refracted ray is getting closer and closer to the boundary here. Eventually, you can get to an angle that is large enough that none of that incoming wave energy makes it down into the second medium. Instead, it bends right at the boundary line, right onto the boundary line. We call that the critically refracted wave, and we call this angle the angle of critical refraction. So when we're dealing with seismic rays in the Earth, as you start to consider the whole Earth, you actually have the velocity of seismic waves changing with depth, which leads to this curving of the ray instead of being drawn flat like I've been drawing them. However, in this class, we're mostly concerned with near surface, and so in most cases, we can approximate our ray paths as being straight through each of the different layers that we're considering. Okay, so again, we have a ray coming in, refracting, and in general, when we're talking about this, we're usually talking about an incident P wave. It refracts at the interface in such a way that here it's bent away from the normal. So again, this is the normal, this is the other angle we're considering, and because it bent away, then the velocity of the second medium must be higher than the velocity of the first medium. Of course, refraction is not the only thing happening at the boundary, okay? You're also having some of that energy reflected. The angle of reflection is always going to equal the incident ray. So these two angles are the same. The other thing that happens at the boundary is that when a P wave is incident upon a boundary, it actually also creates reflected and refracted S waves, okay? So that's now been shown here. You have your refracted S wave and you have your reflected S wave. And this angle is not going to be the same as the incident angle, and that's because the velocity of S waves through the medium is actually not the same as the velocity of P waves through the medium. And we're going to get into the velocities of the waves, what they are and what they depend on in another video. For now, I just want to make sure that we understand all of the different ray paths, right? So you've got the incident wave, the reflected wave, the refracted wave. Both S waves and P waves can be reflected and refracted. And this drawing, however, is only showing you the S waves, and that's because these equations are the ones that you use to determine the angles of the S waves and the angles of the incident and refracted angles of the S waves. Okay, that concludes this video. Hopefully you understand what we mean by refraction, reflection, and conversion. And ideally, you should also be able to use a calculator to plug numbers into those equations in order to determine the values of the angles and the values of the velocities. I hope you found it helpful.